Okay, so I will talk about explanations from our perspective, which I refer to as introspective learning. And I would like to start by giving you this question in here. If I give this to a human and basically tell you this question, why the sign, the traffic sign on the left-hand side, why this is a no left sign rather than a stop sign, right? So now we have a human answer, and if you don't mind, entering your answer into the chat, so we can look at that later on. But what I'm trying to achieve today are really two things. One, to really share with you how a human answers such a question compared to a neural network or a deep neural network. And the second one, what we really get out of this explanation to understand how the machine really answers this question, how can we use these explanations in some other applications? So, and we'll go through a variety of applications that relate to, data acquisition, as well as other, image processing and analysis throughout the talk. Okay. So it's not easy for me to go to the chat, but if you have any answer in here, why the one on the left-hand side is a no left sign compared to the stop sign, please answer it in the chat. Okay. So now, if you look at a typical machine learning or a deep neural network data cycle, then we start from, let me see if I can get the laser pointer so you can see it. Okay. So we can have, we start with data acquisition. We really kind of, adapt the data, prepare it to be processed by data scientists, apply some models, and then we have validation for these models. And then eventually we deploy the model for an end user to use. And then there is a feedback. So the end user has a reaction, has an interaction, or a feedback. It can be natural, it can be much more involved. It depends on what kind of a system that you are deploying. And then that feedback, we can really deploy it back into the data acquisition. And we keep doing this cycle again and again and again. However, this cycle has quite a bit of issues with it. So the simplest one we can think of is the noise. So the data acquisition part noise, there is quite a bit of variation. And when you acquire data from time to time, as it's very obvious, but also when we do the labeling. So we rely on label data in many applications still, and the label themselves, they have some noise, they have some uncertainty in them. And again, the model could be really targeted or poisoned. We have some anomalies, we have some adversaries. So we have quite a bit of a collection. We don't really have a shortage of issues with this within this cycle. And just to share with you some examples from our work in recent years. Let me see if I can get this. I know I'm can't. Okay, so this actually should be a video. Let me see if I can get rid of the laser. And okay, here. So this is basically an experiment we did a couple of years back, and we call it CURE. CURE is challenging unrealistic and realistic environments. Basically, you can imagine we have objects, we have 1 million images. We acquire these images using different sensors at different backgrounds with different distortions. So now you just deploy any ready system to recognize the object. So this is CURE OR. OR stands for object recognition. And then you can, as you already know, as you have more distortion, as you have different, more challenging background, as maybe your sensor is not really as good quality as other sensors, then you start to get quite a bit of wrong recognition. And we have this kind of a data set as a benchmark online. And on the right-hand side, this is what we show for different vendors, as like recognition from Amazon is one of them, for example. And there are quite a few others, like iSpy and others as a benchmark. But it's not really the story. The story is you can do the same thing, but now at a scale for autonomous vehicles, where Now, not only you have sensing distortions, not only you have the complexity of the background, but also now you have environmental challenges. You are on the outside, so now you have, sometimes you have rain, sometimes you have haze, sometimes you have snow, sometimes you have people really kind of, so distortion to the traffic sign themselves. So we came up with this kind of a new challenging data set that can really serve as a benchmark. We call it CureTSR and CureTSD. TSD stands for traffic sign detection, and TSR stands for traffic sign recognition. And we have the benchmark without basically any distortions, but at the same time we have when we add some distortions. And we can really see from many different graphs in here what happens when you increase distortion, either darkening or lens dirt, or more like when you drive with a tree and there is some sun, there's quite a bit of shadow, like on and off while you're driving. That's very, very challenging to the cameras to figure out. Or even snow, for example. We have been working with a Ford Motor Company in Detroit, and they have quite a bit of snow. That's very, very challenging for these machine learning algorithms to operate with certain confidence. So all of this is really kind of telling us the examples of these challenges. And we have quite a bit of data sets on our site on Zenodo if you are interested in looking at our perspective on these kind of challenging data sets. So we have 11 of them in Zenodo if you are interested. So the simplest example is just, this is from years back, and I'm very sure you have seen this in different applications, where even as simple as you have a stop sign and then you just basically kind of change the perspective, the angle, the geometric part of it in the image space, and then you start to get basically quite a bit of very, very, very different class for the traffic sign. As you can see, this is very obviously very, very wrong. And then I always use this very common, very, very popular example in my classes with my students to tell them, you can look at these. There is a muffin, there is a puppy, right? I mean, it depends on what you are looking at. It depends on what time in the morning, if you are hungry or not, as well. That's a very dad joke, but in any case. But the question is, how can we really recognize which one is a puppy, which one is a muffin, as an example? So what we are claiming is that we ask ourselves, we really challenge our own. We introspect. We start to asking ourselves, why am I shown this slide? Why are these images of muffins rather than of pastries? What if the dog in a picture is a bull mastiff? What if the chimp really is in its head? All these questions we keep asking ourselves whenever we see an image. Sometimes they happen without us realizing that we are really asking these questions. And that's basically what I'm trying to formulate explanations in a form of questions. And I'm hoping that I can convince you that we can do the same thing for the machine learning model, and we can really get very, very interesting results. So if you look at the data acquisition piece of it, and this is something I will, at the very end of the presentation, I will share with you just a couple of project that we're really working on right now, how we can use explanation to really drive, I wouldn't say intelligent, but maybe more guided way to acquire new data for our deep neural network and machine learning. So the common one is the supervised and reinforcement learning. That is very obvious work there to really guide data acquisition. What we're really trying to do is to use this explanation within an introspective learning framework for the data acquisition, for the simple reason is that it really hits every single component in the whole cycle of the machine learning and data cycle. So all of these are really sub-bullets, subtopics. I will not really talk about all of these in this presentation, but really the work that I'm presenting today, you will be able to see from our publication, and I'm hoping I can convince you enough in the next like 40 minutes or so that it really hits in every single one of these bullets and more. So let's really start with the model validation here. Let's start by this toy example. And this toy example here, we have a kid, and so now the kid is looking at this image, and this image in here is, I think you can see my laser pointer, is a spoonbill. So all the images I'm showing you in here, they're really an output from a machine learning model where we have an explanation heat map on top of the real image to show you basically what's happening. So let's start with this kid looking at the spoonbill image. And the reasoning mechanism in the kid's head will look something like this. There is a pink feather, there is a straight spoon-like beak, right? You can see it from here. And also there is surrounding water around the bird. So now the kid could really conclude this is really a bird. And in fact, this bird is a spoonbill, right? So this process in psychology and an everyday process, we call it sensing. So there's a visual sensing. I'm sensing certain features, and then I make a decision. So this is a very good example of a feed-forward sensing in this case. Now let's look at something a little bit more interesting, and that's basically the second stage, which we refer to as reflection, right? So in this one here, after the first visual sensing part, now we start to reflect on our conclusion from the first part. And reflection meaning that we are really asking ourselves questions, right? So now we start to have some doubts. Now we start to have some difficulty differentiating the bird from some other bird that come to our head, right? So for example, what if I have flamingo, right? So now, so the kid may ask the question, why this is a spoonbill rather than a flamingo, for example, right? And the answer, of course, is that the shape of the neck is different, right? It's not an S shape. The flamingo will have an S-shaped neck. This one here I have is a straight neck. So that could be one example to answer such a doubtful question. And of course, in here, the kid is really very curious kid, and they will ask, more questions. For example, why the given image is of a spoonbill rather than a pig? Both of them are pink, but why am I looking at this as a spoonbill, not really a pig, right? And of course, as you can see, then this is really a machine learning is telling us the feather part and as well as the beak are really the reasons for that, and the leg as well. Other things like why this is spoonbill rather than the crane, for example, and the machine learning came back and says, oh, because there is no white feathers in here. So these are examples. I will look at some other examples in a minute. But the idea from this is that we are really formulating these kind of questions to really kind of mimic the reflection stage that's really defined in psychology, right? So now, in short, the idea of objectively observing our own thought processes and mental operations in psychology, we refer to it as reflection, right? So now, if we can make all possible sets of questions in the form of YP rather than Q questions, then we may come up with a final conclusion that is robust and is meaningful, right? And then YP rather than Q, the P in this case, for example, Y spoonbill, so that's our class, then the Q is basically our contrastive class, right? And we'll look at this in more detail. So this two-stage mechanism that basically we refer to it as introspection, right? So now, by definition, the introspection in here is really a two-stage reasoning process. One stage is the visual sensing, and the second stage is the reflection stage. And keep in mind, the sensing stage, the first one, is fast and instinctive. The second stage, which is the reflection stage, is much slower and more deliberate, right? In this case. So now our goal from this kind of formulated reasoning two-stage is really kind of to simulate introspection into neural networks, right? And in doing so, we are really making introspection, or we are defining it as answers to logical and targeted questions, right? So now the next natural question is, what would be these possible target questions, right? So here is a set of questions. So the first one, we still have the same image of the flamingo. So if you have a kid, as a curious kid, the questions could be as simple as why spoonbill, right? And then that's why P. So our decision is P. So why P? So this will basically, this question gives you the answers give you about the correlations, right? So we have pink, we have a round body, we have straight beak, then there's a correlation between these features and the spoonbill, right? Or we can go to something more sophisticated with somebody, an expert, and basically the scientist in here is more intrigued by asking the questions of this form: why P rather than Q? Why spoon pill rather than a flamingo, right? So in this case, we have why P rather than Q. So we refer to this as contrastive reasoning or contrastive questions, right? So now the answer could be the lack of the S-shaped neck is really the answer to this question: why spoonbill rather than flamingo? So now so far we have correlation from YP, we have contrastive from YP rather than Q. A third possible question by this fox in here: what if this bird were orange, right? So now, what if? So this is the formulation of the third question, or the type of question we could ask. And the answer could be the neck, the beak, the body, the legs are all different, right? So from a fruit of an orange, right? So it's very, very different. So these are counterfactual questions. So we formulate the questions as correlation question with YP, contrastive with YP rather than Q, and what if, which as basically for counterfactual questions. We can really go even this famous image of from the ImageNet of the bull mastiff in here, right? So each one of these visualization, as you can see in here on the right-hand side, each one of them is really answering a specific question. So the question of why bull mastiff is answered using the face of the dog, and you can see the network is really highlighting the face is exactly the correlation why this is a bull mastiff. And I'm looking at this as observed correlation, observed counterfactual, observed contrastive, because that's what we're really observing in this case. And we'll go in much more detail in the paper about the difference between observed and the true correlations. Anyway, so when asked what if bull mastiff were absent, the network would answer using the features from the cat, right? So this is basically the counterfactual. What if bull mastiff was not in the image? Then basically what the network is looking at is the cat, right? And finally, in here, we look at the network and ask the question, why bull mastiff instead of a boxer, right? Different breed. So the network highlights the heavy, basically jaws of the dog. You can see that, which is really marvelous to observe, right? So now, which is really differentiating this from a boxer. And of course, in here, you can see we have this cat. The presence of this cat in here is also a deterrent for classifying the image as a boxer, right? So now, so this is another example why we are really doing this. Our initial claim that the network is more interpretable. We can really interpret what the model or the network is really doing, but we are really trying to come up with a measure of that interpretability using this kind of questions. And in this case, you can look at observed contrastive question together with causal as well as counterfactual explanation. And what we are really claiming in this paper that these three sets of questions are enough to sufficient to explain all possibilities in a neural network. The three set, basically the observed causal, the observed counterfactual, and the observed contrastive explanations. I will not go through the theory part of it in this presentation, but you are welcome to look at the paper. And here is basically another example. Again, we have in the Stanford data set, we have a Bugatti convertible, and you are asking the question, why Bugatti convertible? And you can basically highlighting the body of the car. But now we say why convertible rather than a coupe? And you can see basically highlighted really the top of the car, right? And all of these are really true outputs from the neural network. And then finally in here, why Bugatti rather than an Audi A6, which is an SUV? And then it's really highlighting the hatchback, for example, and the body of the car. And we have many different examples to show basically how effective this formulation of questions into this giving us this explanation. So now we come to the kind of more of a technical definition of introspective features. So we talked about the goal, we talked about the definition, formulating this into a question. So now we look at given a network of f of x, and we have a datum x, and the network's prediction is y hat. So now introspection into this model f is the measurement of change induced in the network parameters when we have a label, and we call it y sub I. I stands for the introspection here. Is introduced as the label for x. So now I'm pushing this yi as the label for x, and then I'm really trying to look at how much change the model has to do, basically using the gradients induced by the loss function to basically to go from the representation space for y hat to the representation space of yi, right? So that's basically kind of the main core of it, how we can make, and as the keyword in here, we're using the gradients to do that. So here is a toy example to explain this. So we have the MNS data set of the digits, very well known for everybody. So if you have an input 5, this is digit 5 in here, and what we are really showing in these images in here, we are showing the last fully connected layer of a simple 4-layer network, 2 of which are convolutions. And as you can see, we are already asking certain questions, right? So the first one, why 5 rather than a 0, right? And we are really back propagating a loss between the predicted class 5 and the introspective class yi, which is 0 in this case, because this is the yi is 0. We are back propagating, and now we are observing, this is in the inference stage, not in the training stage, this is in the inference stage. And then when we are back propagating, we observe the values only in the zeros, right? In the 0th row and the 5th row, right? So now you can see from here basically that we are really looking at the zeros and the 5th, right? Because we are propagating or looking at how much change between the 5 and 0. And the same thing if we really do, y5 rather than 1, y5 rather than 2, 4, 5 rather than 6, and so on, right? But a very interesting question is this question here, why 5 rather than 5, right? Another way to look at this question is why not 5 with 100% confidence, right? And in this case, what the network did, the network is really believing that some features in the 5 are similar to the 3, to the features in 3. Hence, the loss tends to move the network weights more toward 5 and away from 3, right? And this basically can be seen from the change in the color in the 5th row in here. So the 5 row is in here in blue, and then this one here is yellowish or orange. So you can see basically that we have this kind of formulation of the questions, which can really give you quite a bit of an insight about the data and how the model thinks about the data in itself. A much more actually interesting part in here is that you can see from the information that we are really coming from this kind of backpropagation and looking at the change in the model using the gradients, it's very sparse. So the gradients in this case are very, very sparse, as you can see from these plots in here, right? Which basically means that our introspective features that come from these kind of formulated questions are very sparse, right? And hence they are evidence in such information. Okay. So another very interesting lemma in a paper that we just presented 10 days ago at NeurIPS in New Orleans, to look at the theoretical side of it. But let's look at the robustness element very quickly without going into the details of the math in here. So what we are claiming, basically, these features are also robust, not only sparse, but also robust, right? So now what we did in here, we just take the Taylor series expansion or approximation of a very well-trained network and bring down the loss only to 2 terms, right? These 2 terms in here. So one of which is really conditioned on the predicted class, right? So y hat, and the other one is on the introspective class, which is yi. So now, so if there is any noise, if you have any noise in the input x, in the data x, right? If you have any noise in that input, then we have to have, or there must be a change in the relationship between the yi and the y hat, right? Between these 2 classes. So now if you condition the introspective output on all ingredients, then the noise must break the relationship between n such relationships, because we have n of these classes. And that's why basically we have this kind of robustness. So these features are robust in that element. So what we found out is that backpropagating a vector of all ones, right? So we don't really have to do it for every single, like 1, 0, 0, 0, and then backpropagate, and then do repeat for 0, 1, 0, 0, 0, and backpropagate. Actually, what we found out, we can really backpropagate a vector of all ones is sufficient to extract these features at once. Which means that backpropagating a vector of all ones will give us all the introspective features for an image that we really are interested in for this case. And we show that mathematically in the neuroscience paper if you are interested in more of this details. So what we do, just kind of to put things into kind of an illustration, we have this kind of a network where we produce the introspective features, and we generate these from this base network in the last layer by backpropagating a vector of all ones in here. And then whatever we get the output from here, basically these are our introspective features. Now, this is a very well trained network, right? And then we have a vector of all ones at the end. We backpropagate it, and then now we have our features, which are basically the gradients, that how much change the network has to do. Now, what we could do with this? So basically these features in here, right? So now what we could do with these gradients? They are the second one I really wanna, or the second goal of my talk today, is to convince you that basically there is a lot you could do. We split this into two things. On the left-hand side, you can really use these features directly into your application. It could be adversarial image detection, out of distribution detection, corrupted image detection, opposite recognition. The list goes on and on. And I will just talk about one or two of these experiments in here. Or you could really use it as an input to another network. The claim in here that we are really making is that introspection can be just a plug-in on top of any other network that you are already working on. And we'll show some examples on, like a robust recognition, but I will spend some time on the image quality assessment part because it really gives us quite a bit of interesting analogies between the human vision system as well as the machine vision system. So let's start with the left-hand side. So let's look at this out of distribution detection. And I'm hoping while we are really highlighting these experiments, you can kind of have a feel of how we can use these introspective features. And remember, I want you to remember, introspective features are really coming from answers by the network to our three types of questions, right? Okay, so we have a very basic experiment in here. We have a training set. So we have a resonant 18 model. We train it with MNIST data set. And then we collect the gradient information by using a confounding label on MNIST test set as well, right? So the other data sets in here are very different in the domain, right? So we have the SBHN, we have Cypher10, we have Tiny ImageNet, and then we have LSUN in here. You can see the SBHN has digits, but the other three, they are very different in nature from the MNIST, right? And then what we do, we really compare the gradient-based representation for MNIST, that's basically, we call it in distribution, as in the blue, right? Versus the LSUN, which is basically in the orange in here, or brown, depends on how you can see it from your monitor. Okay, so the x-axis is really showing the network parameters of the resonant 18 from the first convolution all the way to the last fully connected layer on the right-hand side. And the y-axis in here is the L2 norm. So this is the L2 norm of the gradients representing the distance of the space of the model. So now the values that we are showing in here are average for each predicted class for more, better presentation. And as you can see in here, the range for the L2 distance or norm for the out of distribution, the LSUN, is much higher than the in distribution MNIST, which is really kind of what we expect, right? In here. So we validate basically this kind of shift or this introspective features or how much shift the model has to do for this distribution input in the inference stage using some kind of a standard experiment in the OOD literature. So we validate this using, as a measure for uncertainty for OOD detection in a larger kind of scale. So we utilize the Cypher10 and SBHN data sets as in distribution, and that's what we have in the N column in here. And then the as distribution for the Cypher10, we have the other 3 data sets. For SBHN, we have 3 other data sets. And then now we have detection accuracy, we have AOROC, and then we have the AORP, which is area under precision recall curve. And then we compare basically different our method with other widely used basically methods. So we have the baseline, the first number, we have Odin in the second, we have the Mahalanobis in the third one, and then another version of the Mahalanobis in the fourth one, and then our method is the last one on the right-hand side. So you can see in all of these cases, our method actually, not all of them except basically when we have a tiny image net in here is different, but in all the other cases, we're really kind of getting better results than the other methods. But actually, the more interesting part is to look at this part in here. Why are we getting really kind of a better results when we have SVHN as the end distribution, but the other ones are the Cypher10, tiny image, and LSON in this case. So the SVHN, which is our end distribution network or distribution data, is a simple data set consisting of just basically, just very simple digits with certain backgrounds in here, right? So it doesn't really have that kind of requiring, like a real image of objects like Cypher10, tiny image, and LSON in this case. And that's why basically our method, that's basically which is measure the change for this out distribution one, very different from the in distribution. The model has to really change quite a bit. So that's where our method really kind of capture that change quite a bit and gives us really better results in here compared to when we have the in distribution as Cypher10 in this case, as you can see in here, right? So that kind of why we have a much better improvement in the performance here compared to when we have Cypher10 as the input, because Cypher10, for example, compared to the tiny image net, they're very, very similar in that sense. And the LSON, SVHN, a little bit farther away from these 2 data sets in that case. So it depends on how much change you are looking at. We have a much more kind of ablation studies in this paper if you are interested in looking at this ablation study. Similarly, if you look at adversarial input detection, right? So, and this is a very famous example. You have you look at this as the network will tell you this is the panda with 57 confidence, and then if you add just a very tiny noise to it, and then it gives you this image in here, then the network will think this is a gibbon with a 99% confidence. That's a problem. That's a very serious problem that we have in here. So now this makes it very difficult to ensure reliable performance of network for practical applications. And what we are really trying to propose in this paper in here to examine the ability of the trained neural network to handle input during inference using the representational power of the network established by the training data set that we are using. And all of this could be done using the explanation and the formulation of the question that I presented earlier in the last 20 minutes or so. So for these experiments, we utilize the gradient-based representation generated with confounding labels to a trained sample of a very simple 2-layer MLP to detect anomalous inputs of adversarial attacks as distribution, right? So, and you can see in here, this is the last column of our method compared to the other methods in here. We're really doing, on overall, a better job, sometimes by even 20% improvement compared to other methods, or 10% improvement to the best of these methods, for example. But a more interesting experiment to look at this corrupted input, right? That's I started that presentation with. So we have Cypher10C, which is a Cypher10 with very different corruptions: Gaussian noise, defocus blur, Gaussian blur, fog, snow, and brightness. And we have the one I mentioned earlier, QTSR. We have traffic signs recognition, but also we have decolorization, we have lens blur, we have dirty lens, we have exposure, noise, snow, haze, and so on, right? So now what we do in here, we compare our approach with the Mahalanobis method, right? And we have two data sets. So we have Cypher10C and then we have QTSR. Let's look at the Cypher10C, right? So if you look at the performance in here, yes, we are getting 99, 100%. But quite frankly, if you look at the performance, we have quite a bit of saturation happening in here, right? So we have it's still outperforming by some degree the Mahalanobis, but still overall we have some saturation happening in this case. In contrast, if you look at the QTSR dataset, and if you look at low levels of noise, so level 1 means little noise, level 5 is very, very bad noise added to the image. So if you look at the low level noise, level 1, level 2, our method of measuring how much change in the model or the model has to change in the inference, how much the model has to change in the representation space to accommodate the input, the corrupted input, is actually giving us quite a bit of improvement in the performance compared to the Mahalanobis, as an example, sometimes by 40% or 30% improvement in this case. So it's actually our method is much more effective when we measure the change. Is much more effective in detecting corrupted input when we have a low severity noise added. As the noise becomes higher and higher, then actually the gap between the two methods is smaller and smaller, and sometimes even you cannot really tell the difference between them as we saw in the Cypher10C in here. And that's actually very, very interesting results that we are sharing in here. Now, let me go to, I hope that there are many, many different algorithms or applications where you could use the answers to these questions into applications. But a much more interesting part of the presentation today is this one on the right-hand side, how we can use this plug-in approach on top of other algorithms. And here is basically what I'm referring to. So the introspective features that I used or showed you, the one on the left-hand side before, this method in here, or this block in here, we can use basically backpropagate all ones. We get these features, which is basically how much change, these are the gradients, how much change we need to anchor into the model. And then we use these as our features. And now it could be the second network, and here could be anything. So in this example, we are using a very simple MLP network, and then we input to it these features. So these are the introspective features really coming from the first network. These are 3-layer MLP in this paper, just to kind of demonstrate the effectiveness even using a very simple network like this. So now this introspective network is different from the introspective features. So now the input in here are the introspective features, but now we call this as an introspective network that we're really training with these input features. So now the extracted gradients, right, features are both, as we claimed before. Remember, I claimed that these are sparse as well as they are robust, right? And we utilize these properties to state or to claim that introspection provides us a robustness when the train and test distributions are different. And how we define robustness in our work, we define robustness as being both generalizable as well as calibrated to new data. That is out of distribution compared to the training set. So we have generalizability and we have calibration. So generalizability implies that we have an increase in accuracy even when the out of distribution data is not seen during training and only shows up at the inference stage. Calibration, it really measures the difference between the confidence levels and the prediction accuracy, right? And we'll just show you basically kind of these results in here. So we have the Cypher10C on the left-hand side. We have the Cypher10Q on the right-hand side. So we have two data sets. The Cypher10C has 19 distortions and 5 levels in each distortion. And the Cypher10 cure 6 distortions and 5 levels in each distortion. The x-axis in these plots is the expected calibration error, or ECE for short. The lower this error, the better it is, right? And then the y-axis is the performance accuracy. So the higher the accuracy, the better it is, right? So in that case, the top left corner on these plots is the ideal corner for any network that we are really working with. So in this experiment, we look at 4 different networks: resonant 18, resonant 34, resonant 50, and resonant 101 or 101. So the base networks, all right, and this is basically, we are showing it in the variations of red. See the 4 networks in here, the 4 networks. This is basically, these are networks that have been trained on these data sets and in this data set in this case, and we are really looking at the ECE and the performance accuracy, and that's what we are really showing in here. So we have no introspection whatsoever. But now if we add the introspection features and we train the 3-layer MLP on top of these networks, then all of these 4 points, they are moving left and upward. This one's much more obvious, they move left and upward, right? So actually, on average, we have witnessed an improvement in the accuracy by, on average, by 4%, but the improvement in the calibration is north of 40%. Around the average is like 42% in the calibration. So introspection actually is give you this kind of a much more generalizability as well as calibration in this case. Again, I'm making the claim in here that this introspection network can be just a plug-in, and you can really plug it in on any existing state-of-the-art methods, and you can show basically the performance in here. So we are showing the state-of-the-art in here, you know, for denoising, for SimCLR, for augments, for example. And the first number is the feed forward, and the second number is the introspection, right? So in this case, basically, it gives you a little bit of improvement, but in the other ones, it gives you quite a bit of improvement. So, but again, this is accuracy, but when you look at the calibration is really give you much higher confidence in the performance. Again, we claim any downstream task that really benefit from generalizability and calibration will benefit from this method, from this introspection or 2-stage explanation network. So we show basically in our paper, we show if you look at active learning framework, actually there's quite a bit of improvement in that scenario. And I will talk more about the image quality assessment. So even the image quality assessment method, we have quite a bit of improvement. We have the unique that we proposed, an unsupervised neural network from years ago. And then when we just add to it introspection on top of our unsupervised image quality assessment, we really get an improvement in the performance in here. And again, for other distributions. So let me talk a little bit about the image quality assessment, because it's really very interesting. So in case you are not really familiar with image quality, we have the image on the left-hand side. So we are really trying image quality assessment. We're really trying to assign a number between 0 and 1 that really gives us especially what is the quality of this image, right? So imagine that we have this image on the left-hand side. We have a lighthouse image with level 5 lossy compression from the TID 2013 dataset. And we use this method in here to give us a score. And it gave us a score of 0.58, right? So this is basically an image of an okay quality, right? So now what we do in here, we first use the GradCam as it is. Basically, this is the answer to the question, why 0.58, right? And you can see basically we look at the highlight, what the feature map on top of, sorry, the heat map on top of the image, and basically highlighting basically where are the parts in the image that contributed this quality of 0.58. So now you can see from here that the lighthouse in here is basically kind of, you know, is giving us some of this. So what we could conclude from this heat map is that the quality score was decided based on all parts of the image, foreground, background, but the base of the lighthouse is basically kind of, you know, contributed the most to why we get this 0.58. So now let's reformulate the question to say, why 0.58 rather than a 1, right? Why didn't I get a 1 in here? So now we have a, remember what we do in here, we have a loss between the predicted score of 0.58 and the contrast, which is 1. And then we are back propagating that. And then we are visualizing where in the image basically we have to the change. So basically the visualization is grad cam feature heat map on top of the image again. So now what you can see in here, all the foreground portion of the image, like house, lighthouse, and the cliff are highlighted, right? So this means that distortions in these foreground objects prevent the network from predicting a high score of 1, right? You can make it even more interesting to say, let me now be a little bit, more conservative and say, why 0.58 rather than 0.75, not 1? And you can see basically now I'm using the structure of the building in here as well as the lighthouse, but not the cliff anymore compared to the previous one. So this, especially these ones, contributed to the fact that this is 0.58, not 0.75. You can go to the other side to saying, what about 0.58 rather than 0.5, right? It's lower, right? So now, why did the network predict the 0.58 rather than a lower score of 0.5, right? So the network in here actually, for the first time, is highlighting the sky. You can see this is the first time the network is saying the good quality of the sky and the lighthouse lead us to believe that the quality is higher than 0.5, right? You can even go further and say, why 0.5 rather than 0.25? And basically you say that the score is really higher than 0.5 because the great quality of these parts of the image in the sky, the lighthouse, and so on are really kind of contributing this high quality. And we can really do quite a bit. So we show this in a paper in much more details. And what's really interesting in here, or the conclusion that the network basically kind of, by itself, without training the network to do any image quality assessment, the network actually learned by itself the image quality assessment rules. And all what we did, we just extracted basically these user questions to highlight that the network really learned the image quality assessment rules in here. Of course, that's a very broad statement, but there has to be much more comprehensive study about what else in saliency and image quality assessment. And we start to, in the last 2 years, to look into these directions to figure out what the network has learned in these principles. So we showed this, actually we can brag a little bit. This was the best paper award in 2019 in ISEP because it really gives us kind of that kind of trust a little bit into the network that it really learned a little bit of what the human vision system is doing. Very quickly, actually, I want to just spend like the next 5 minutes before I stop about this model. I spent quite a bit of time about validation, and now I'm going to spend a little bit about the training part of the model. So we use basically anomaly detection to kind of, as an experimentation. Can we use the gradient to give us basically kind of anomaly detection into our data? So we'll go through maybe just the illustration here. So I mentioned the gradients quite a bit in my presentation, but here's basically what kind of a geometric or illustration of it. So if you have your manifold, right, and it's in the blue in here, and you have an anomaly data point X out in here. So now, if you use the reconstruction error, it will measure basically the distance between this data input and its projection into the manifold space, right? So what we are really doing by looking at the gradients, we're really trying to say, we have the model, how much I need to deform my model, my representation space, right, in order to include that point into my space, right? So how much I need to do in that case. So that's why using the gradients, it gives you how much you have to deform and in which direction. So we have a direct direction as well as we have a distance. So that's why you can see basically we have the cosine similarity, it gives basically the direction in this case. And we have much more details about why the gradients are really kind of the way to go in measuring that change. But I will not really go through the details in here. Okay, other things where this becomes very, very effective. This is a very recent experiment that we presented at the New Europe's last week. Um, um, when you have OCT scans or X-ray scans or some kind of an image scan for human body case, and can we use the gradients to give us kind of an approximation of how severe the disease is? Like in this case, basically we have diseases in the eye, we have the OCT, and we worked with a ophthalmologist clinic in Houston, and it's amazingly how the gradients can really kind of give you the ability to create a scale of severity. And actually that really produced this. If you are interested, we have this new data set from the ophthalmology department in Houston, but now we have the benchmark with also all the different biomarkers and basically human label from the doctors in there if you're interested. Again, in all of this, we're using the same technique, how much change the model has to do to adapt to the severe cases. I will not go through the cases in here. And finally, to close what I started with, two things. One, how can we use this in guiding our data acquisition? So we did this with the Houston data clinic, eye clinic, and actually it's a much larger than the OLIVE data set. It's a multi-model data set, and actually it's all guided by the what if, why B P rather than Q, why P, and what if questions. And also we are about to release a new data set. It's a very, very huge data set by collaborating with autonomous vehicle department, Ford Motor Company, that basically has, it was all guided by this gradient change and the 3 type of questions with all the annotations. But this will be in public very, very soon in 2023. Okay, let me go back to the first question I asked you. Why no left sign rather than a stop sign, right? So this is a no left sign. And the question I asked, why no left sign rather than stop sign? So if you were me, I would say the difference between a stop sign and the no left sign is the letters, the STOP, right? STOP, basically, it's very obvious for us as a human. It's not, it's a stop sign. This one has no STOP. So I expected the network cite basically the fact that I don't really have STOP. However, the network is already highlighting this part. So saying this part in the no left sign is the reason why the network decided to say this is the no left sign, not a stop sign. So that actually gives us the idea that it's not always whatever the network is showing us is the human interpretable in this case. And if you look more carefully, why the network did this, why the network relied on this part, it goes back to, which I always claim, maybe people don't like it, but the network is very lazy. It will try to find the shortest cut to make a decision. And if we really inspect the training data set, the training that we used, these are a traffic sign, right? If you look carefully at all these traffic signs, right, they're all basically round, except for the stop sign. The stop sign is the only one that has a diagonal in here, right? And compared to all of them except the triangle one here. But if you look at the lower left corner, there is the only basically line in all these traffic signs is the stop sign. And the network basically just said, okay, that's enough to tell me that this sign here is not a stop sign because this one here is on a straight line. It's not the best basic kind of, I'm not sure if I want to rely on that kind of decision, but this is very important insight into how the network behaved in this case. So I'm hoping I achieved kind of, the two goals that there are some overlap between how the human look at explanations and how the machine look at explanations. We use the image quality assessment part. At the same time, how features that come from explanations can be extremely effective either in applications or in kind of as a plug-in approach, as I showed you in the image quality assessment as an example. Before I conclude, I want to really accredit the work to our postdoc, Dr. Mohit Prabhshankar, our alumni, Gokyung Won, who's at Amazon right now, and our current student, Jinsol, Yashi, and Ryan for all their work. And sorry, it took me 7 more minutes than I had planned. Thank you.